Hi everyone, welcome back to another video on this channel. In this video, I will show you that how to obtain Thevenin's and Norton's equivalent of any complicated circuit when the dependent source is present. In the previous videos, whether it was on Thevenin's theorem or Norton's theorem, I had taken the examples where we had only independent sources. In that case, in order to find out RTH or RN, we replace the ideal voltage sources by short circuit, and the ideal current sources, they are replaced by open circuit. And I'm saying all this about the independent sources. Whenever we have dependent source, we have no idea about their internal resistance. So it's not possible to replace them by open circuit or short circuit. And the method which we adopt to calculate the equivalent resistance seen from the load terminals by replacing the sources by their internal resistance is not applicable. So when we have the circuit with dependent sources, in that case, how to find out RTH or RN, that can be calculated by taking the ratio of open circuit voltage to short circuit current. So this is the one way by which we can calculate Thevenin resistance or Norton resistance, and also we can have the value of open circuit voltage which is used to draw the Thevenin equivalent. We can have the value of a short circuit current which we need to obtain the Norton's equivalent. So what I want to say over here, that when we have dependent source present in the circuit, at that time we need to obtain both open circuit voltage as well as short circuit current, and hence we obtain the Thevenin's equivalent. So I will show you this with the help of numerical examples only. I am starting with the first problem, in which what we need to do, a circuit is given. Here we have a dependent source. Now this is a 2 ohm resistance through which current I2 is flowing, and across these terminals voltage is Vi. Question is, for the circuit shown in figure, find the current through 2 ohm resistance. Now which 2 ohm? This is also 2 ohm. Now basically it's about current I2 using Thevenin's theorem. So when we need to find I2 using Thevenin's theorem, means this 2 ohm resistance which is connected between these two terminals, that is a load resistance. Let's mark them A as B. Now to obtain the Thevenin's equivalent, we need to calculate open circuit voltage and we need to calculate the Thevenin resistance. So first step is calculate VOC. So when we start calculating VOC, here we have a voltage dependent voltage source its value is 4 Vi minus plus Vi. These two terminals should be open circuited, A, B, and we need to find out the voltage between these two. This is VOC. Source is supplying 5 volts. Now the two circuits are different, so instead of writing it as Vi, I will write this as Vi dash, and same will be reflected over here since it is a dependent voltage source. It's voltage dependent voltage source. The output voltage of this source is controlled by this voltage Vi. Now from here the circuit is open. Circuit is also open from this side. So the current through this 2 ohm resistance is 0. We can apply KVL in this open loop. This will be the path. We can apply KVL over here. So when we apply KVL starting from VOC, here VOC plus 4I, 4 Vi dash equal to 0. So VOC is equal to minus 4 Vi dash. We need the value of Vi dash to calculate VOC. Again, KVL is applicable to this open loop as well. We can apply KVL here. So when we apply KVL in this open loop, the drop across 2 ohm resistance is 0. Then we have minus 4 Vi dash minus 5. Again the negative sign came first. Then the voltage across this open loop is minus Vi dash, and this equal to 0. So answer for Vi dash is minus 1 volt, which will give us the value of VOC as 4 volts. So VOC is 4 volts. We got the answer for Thevenin voltage because this VOC actually VTH. Now next step is we need to calculate RTH. Since we have this 4 Vi source over here, we have no idea about its internal resistance, so we can't replace it by either open circuit or by short circuit. When it's not possible, so what we need to do, we need to find out the short circuit current as well in order to calculate RTH. So second step is calculate ISC. Now for calculating ISC, we have to replace the load resistance by short circuit. Terminal A, B, in between terminal A and B, we have to replace it by short circuit. We need to find out that what is the current through the short circuit. 2 ohm resistance. Here we have minus plus Vi. This is 4 times Vi. Again, the circuit is different from the initial case where the voltage was Vi. Since the circuit is different, we had replaced this 2 ohm resistance by short circuit. So this will not be no longer Vi. Let's denote it by Vi double dash, and same should be reflected over here. Now the current through this 2 ohm resistance is ISC, since the ISC follows this path. Will follow this path. So we have the drop across 2 ohm resistance. This terminal will be positive, this will be negative. Now when we apply KVL to this loop, we have 4 Vi double dash plus 2 into ISC equal to 0, or ISC is equal to minus 4 by 2 Vi double dash. So basically we need the value of Vi double dash to calculate this. For that, what can we do? We can apply KVL to this open loop, starting from 5 volt source, minus 5 minus Vi double dash. Then for drop, as this sign is negative, so it's minus 2 into ISC minus 4 Vi double dash equal to 0. Since we are interested in finding out the value of ISC, in this equation, which is now 5 Vi double dash minus 2 ISC, let's replace the value of Vi double dash by ISC. Now Vi double dash from here, it's minus ISC by 2. So minus 5 minus plus ISC by 2 minus 2 ISC equal to 0. 5 ISC minus 4 ISC equal to 10, or ISC is 10 ampere. So we get the answer of short circuit current. Once we have the value of open circuit voltage and short circuit current, then we can calculate RTH as VOC upon ISC. VOC was 4 volts, ISC 10 amperes. So RTH is actually 0.4 ohm. And the question was that we had to find out the current through 2 ohm resistance using Thevenin's theorem. So we have to draw the Thevenin equivalent of this circuit, in which we draw a voltage source in series with the resistance, that is Thevenin resistance, 4 volt 0.4 ohm, and in between the load terminals AB we have to connect the load resistance back, that was 2 ohm. So I2, that is the current through 2 ohm resistance, is 4 upon 0.4 plus 2, which is 1.67 amperes. So this is the answer of current through 2 ohm resistance using Thevenin's theorem. In fact, it's possible to draw the Norton's equivalent as well. Since we had done all the calculations, we can draw its Norton equivalent as well. Norton current is 10 ampere. This 0.4 ohm resistance, it should be connected in parallel, and in between terminals A and B we have 2 ohm resistance. And if we want to find out the value of current I2, then it will be equal to source current into opposite branch resistance upon opposite branch resistance plus the load resistance. Now this expression and this expression both are same, so answer is exactly same by the two theorems. So this one is Thevenin's equivalent, while this one is Norton's equivalent. Now this method for finding out RTH, that is by ratio of open circuit voltage to short circuit current, is equally applicable if we have the circuit without without the dependent source. Means when we have the circuit with only independent sources, at that time also this method is applicable. So you can use this one if you want, otherwise you can go with the method which I had described earlier. So you can check the method that how to calculate RTH or how to calculate RN in the previous videos, and the link for them is provided in the description box. Now coming to the second problem. Second problem is obtain Thevenin's and Norton's equivalent for the given network across terminals A and B. Here we have a dependent source, which is actually a current dependent current source. And these are terminals A, B. Since we have to find out the Thevenin's and Norton's equivalent, we need to find out open circuit voltage, short circuit current. Their ratio will give us the value of RTH. So let's start calculating VOC. For calculating VOC, circuit is same. There will be no change in the circuit. So whatever the voltage is there across the current source, same is the voltage across these terminals AB. This is VOC. Since there is no drop from A to this and B to this terminal, so if we find out that what is the voltage across this current source, that is actually open circuit voltage. Now how can we find out this? We can consider that this is our reference node and the node is at voltage VOC with respect to reference. We can apply KCL from this side. Current 2I1 is coming from this side. Current is I1, and on this side, since there is open circuit, so I1 plus 2I1, it is equal to 0. Sum of incoming currents is equal to sum of outgoing currents, and outgoing current is 0. Now let's write the value of I1 in terms of VOC. I1 is flowing from reference to node 1. So I1 will be equal to 0 minus, then we have the voltage source. On reference side, we have negative terminal, so it will be considered as minus 8 minus VOC by 4, which will give us the value of I1 as 8 minus VOC by 4. Now when we use this value of I1 in this equation, we have 8 minus 4 VOC, sorry 8 minus VOC by 4 plus 2 into 8 minus VOC by 4 equal to 0. The solution of this equation will give us the value of VOC as 8 volts. See, we got one answer. Next is we need to find out the value of short circuit current. For finding out short circuit current, we need to draw the circuit again. So when we draw the circuit again, now the terminals A and B, they should be short circuited. We will find out that what is the current through this short circuit. Now the circuit configuration is different from the initial case. This I1 is not same as what we had calculated over here. Though the formula, you can write it in terms of node voltage, that you consider that voltage over here is something like V, then you can write it as 8 minus V by 4. But since the circuit is different, it will become a different quantity. Let's denoted by I1 dash, and that has to be reflected over here as 2I1 dash. Now if you want to find out ISC, here if you want to apply nodal analysis, it's not applicable since through terminals AB the resistance is 0. We can't write the current through this. So we have to adopt mesh analysis. In mesh analysis, we have two currents. In this side, we have already current I1, so I am assigning this one as I1 dash. In this, the current flowing is ISC, I am assigning it as ISC. Now, when we apply KVL, since a current source is common to both the meshes, KVL is not applicable to individual meshes, but they have to combine together to form a super mesh. So the equation of super mesh will be, starting from this 8-volt source, minus 8 plus 4I1 dash equal to 0. So the value of I1 dash from here is 2 ampere. Then the constraint equation for the super mesh is the resultant current through this branch should be 2I dash, and it should be in upward direction. So in upward direction we have current ISC, I1 dash is in opposite direction. So I dash is equal to ISC minus I1 dash, or ISC is equals to 3 times I1 dash. I1 dash is 2 ampere, so ISC is 6 amperes. This is how we get the value of short circuit current. Now once we have the value of open circuit voltage and short circuit current, now we can calculate the value of RTH or Rn, which is actually ratio of open circuit voltage to short circuit current. 8 by 6, that is 1.5 ohm. Now question was that we have to obtain the Thevenin's and Norton's equivalent. So if it is asked that obtain the Thevenin's and Norton's equivalent, we always need to draw them. It's not like that we leave over here and we say that the problem is over. We need to draw the circuits again, their equivalents basically. Thevenin equivalent is voltage in series with RTH, terminals A, B. So this is Thevenin's equivalent. And 6 ampere in parallel with 1.5 ohm resistance between terminals A and B is Norton's equivalent. Let's take one more problem, which is going to be the last problem in this video. Question is again same. Obtain Thevenin's and Norton's equivalent for the network shown in figure across terminals A and B. So let me draw the circuit for which we have to obtain the Thevenin's equivalent. 2 volt source, 2 ohm resistance, 2 ampere, 1 ohm resistance, minus plus 4 Vx A and V, and Vx is the voltage over here. So here we have a voltage dependent voltage source. We need to obtain Thevenin and Norton's equivalent. Again, we have to find out open circuit voltage and short circuit current. For finding out open circuit voltage, let's draw the circuit. I need to copy this again. These two terminals are already open. Let's assign the voltage polarity like this. This is the assigned polarity. Now, how to find out open circuit voltage? We can find out open circuit voltage by applying KVL to this open loop. Here voltage is Vx. If this one is reference, then we can find out the VTH by applying KVL to this open loop. So for that we can write it as minus Vx minus 4Vx equal to, not equal to, plus VOC equal to 0. Reference means negative, this side positive, so Vx minus Vx, then drop across 1 ohm resistance is 0, since this is a loop which is open. It's an open loop, so drop across 1 ohm resistance is 0. Then minus 4Vx plus VOC equal to 0, or VOC is equal to 5 times Vx. Now we need to find out the value of Vx. How can we obtain the value of Vx? Vx can be obtained by applying KCL at this node. 2 ampere current is incoming. We don't know what is the current in this branch. Let's say it is an outgoing current. Current through this branch is 0, since from here the circuit is open. Still we can apply KCL that sum of incoming currents is equal to sum of outgoing currents. 2 is equal to Vx minus 2 by 2. Vx minus 2 divided by 2 is the current in through this 2 ohm resistance. So this will give the value of Vx as 6 volts. So once we have the value of Vx as 6 volts, then open circuit voltage, which is equal to 5 times Vx, that becomes 30 volts. So Thevenin voltage or the open circuit voltage is actually 30 volts. So we are done with the one step of this problem. We obtained the value of open circuit voltage. Second is we need to obtain the value of short circuit current. For obtaining short circuit current, Let's draw the circuit again. I'm just pasting it. The low terminals, that is terminals A, B, they should be short circuited. Mark that current as ISC. Now, since the circuit configuration is different, this Vx will now change to another voltage. Let's denote it by Vx dash, and same will be reflected over here. You can't use the value of Vx as 6 volt which you had calculated for finding out open circuit voltage. If you use the value of Vx as 6 volts in this case as well, then that will be a wrong approach. Since the circuit configurations are different, so we have to show that change in this controlling quantity. So now this is the circuit, this Vx has now become Vx dash. ISC, that is the current through AB. So basically that is the current through this 1 ohm resistance. So we can write the value of ISC as, considering this as reference node, as Vx dash minus of 4 Vx dash minus 0 by 1, or ISC becomes 5 times Vx dash. Now we need to calculate Vx dash. How can we calculate Vx dash? By applying KCL at this node. Now when we apply KCL, 2 ampere current is incoming current. We don't know the direction of current through 2 ohm resistance. I am assuming it as an outgoing current. Same over here. So sum of incoming currents, that is equal to sum of outgoing currents as suggested by Kirchhoff's current law. Current through this 2 ohm resistance is Vx dash minus 2 by 2. Vx dash minus 2 by 2 plus current through 1 ohm resistance is Vx dash minus of 4 Vx dash by 1. 2 equal to Vx dash by 2 minus 1 plus 5 Vx dash. So which will give us the value of Vx dash as 6 by 11. It's 6 by 11 volts, and hence the short circuit current, which is actually 5 into Vx double dash, it becomes 30 by 11 amperes, which is actually 3.727 ampere ISC. So once we have the value of ISC and VOC, we can calculate RTH or R Norton. Both are same as ratio of open circuit voltage to short circuit current. We found the value of open circuit voltage as 30 volts. Short circuit current is 3.727, which gives us the value of Thevenin resistance or Norton resistance as 11 ohms. Now we can draw the Thevenin and Norton's equivalent. 30 volts in series with 11 ohm, terminals A, B. So this is actually Thevenin's equivalent. And current source of 2.727 amperes connected in parallel with 11 ohm resistance across terminals AB is Norton's equivalent. So this is how we obtain the Thevenin's and Norton's equivalent when we have dependent sources present in the network. I'm hoping that these problems are helpful for you in understanding the concept of Thevenin and Norton. I will take a few problems in the next video as well using the same approach so that you can have the practice of these two theorems. If you find this channel helpful, please consider subscribing it. Thanks for watching the video.